Alright, welcome. In this video, I want to start talking about reinforcement learning. And reinforcement learning has a very long history going back to the 1950s and even earlier. And we're going to start around the 1950s talking about the idea of utility maximization. And we're, for the moment, going to do that in deterministic environments, keeping open the possibility as we progress down this path towards stochastic environments or randomized environments where there's maybe some probability or uncertainty involved. The field of reinforcement learning really gets its inspiration from the idea that in any given moment, any given agent is basically trying to do the same thing, which is just decide on what to do. What is the action that you should do next? So this, as a jumping off point, is sort of the place where we're going to begin our task. So any agent is trying to decide what they're doing in the moment. Let's assume for the moment that these agents have some kind of deliberative capacity like we do, and they want to decide what it is that they should do. So we know that from the types of agents we've been looking at so far, for instance, the agents we looked at in the evolutionary robotics models, with their neural nets, they were reactive agents. They would get some input, some stimulus in through their sensors, and they would immediately translate that into output, that is, how fast their wheels would turn. And this meant that there wasn't any deliberation between them. They just, sensory input gets turned through some neural processes automatically into some wheel outputs, and that means that these agents aren't sort of remembering anything or making choices based on their history. These are things that we can build into our agents if we wanted to, and they're certainly things that normal biological agents do. One thing that our evolutionary robots didn't have is they didn't have a reward system built in, but in most biological agents, there is a reward system that is built in. That is, we get signals from the environment, pleasure and pain, that help us regulate our own behavior and recognize things as either good for us or bad for us. So another way that an agent might be able to make decisions about what to do next is they might deploy their understanding of the world. We usually call this as a model to predict the outcome of their actions. So my robot here says, force equals mass times acceleration. That's sort of that's Newton's first law. That's one way we can predict the outcome of our actions, but most human beings don't sit down, get out their pencil, calculate forces and masses and accelerations. We have something also built into our neural nets, which we usually call folk physics, where we would say that our ability to throw a ball, catch a ball, run and stop ourselves before we run into a wall or something like that. All of these abilities, we don't actually do the explicit calculations, but we are somehow doing the implicit calculations in our neural nets. And so in that sense, we might have an implicit model of the world that we might use to predict the outcome of our actions and our behaviors. We might also have in mind specific goals. We might know where we want to go. Maybe we know we want to go to Hawaii. We might also have built in tools or techniques to evaluate states or possible situations we might find ourselves in. We might evaluate them using some kind of standard of judgment. In reinforcement learning context, we usually call this a utility or utility function. So we might think that Hawaii is a good potential goal state because we've heard good things about it. It's warm and there's a beach and so on. So we might use these to determine what are the things that we want to seek out in our actions. So in doing our action, what is the state that we are trying to achieve? And then when we're making our choices, we may have to deal with uncertainty in the environment or in our own actions, and this just means that maybe our model is incomplete, so we don't really know what the world, how the world operates yet, so we're not certain what the outcome of our actions are. Or maybe we have a pretty good model, but that model tells us that certain actions are unpredictable or unreliable, and so even though we might want to win the race, we might not be able to win the race. So reinforcement learning, as I mentioned, sort of uses this as a jumping off point, this idea of choosing what to do next, and uses that to try and build algorithms or learning methods that are going to take the feedback that's given through environment, again, reward or punishment, we call this the reinforcement, and use that through a process of trial and error to maybe learn what the best action is for us in particular states or particular situations. We are again inspired by the idea that that's something that we see animals doing and humans doing. We seem to learn through trial and error and through the feedback provided by our environment. So if we can, extract that same ability and put it into some of our agents, then maybe they'll be able to learn some interesting things as well. Another thing you might notice is that reinforcement learning is another example of unsupervised learning. So in the last couple of videos, we've been talking about neural nets and training them through back propagation. And that process requires supervised learning, meaning we need to know what the expected output is going to be for our agent, in this case a neural network, to train it. In reinforcement learning, we use the environment more as the trainer. We use the shape of the environment insofar as us navigating around it, moving around, finding different things in our environment. We use that to our advantage to learn about what that shape is. And then we also use, as I mentioned, the feedback or the reinforcement we get from the environment. Maybe that's the pleasure and the pain that we may feel when we carry out certain actions in that environment. So let's take a look at a very simple kind of agent environment to get started, and we'll sort of add complexity to this as we go. At the moment, as I mentioned before, this is sort of just a toy environment that is going to potentially have some expansion. So at the moment, this is a finite and discrete environment. So there's only a finite number of states here. It's a very small number. And then they're also discrete, meaning we're in the state or we're not in the state. We can move from one to the other, and we can't be in half of a state or outside of this environment. We can imagine there being infinite environments or ones that have continuous states. So we can sort of slip and slide in between two cells. But again, for the moment, we're going to stick with finite and discrete states. So just for simplicity, I've just put an overlay here where I've maybe given some names to these states in case we need to talk about them later. Although visually we probably don't need this. You'll notice there's one state here that is not going to be a state that the robot can occupy, so we're not going to look at that one. The pit of spikes and the pot of gold, those are what we call terminating or final states in our environment. If we fall in the pit, we assume that we're going to die. If we get the pot of gold, that's what we're trying to get. That's our goal state. So we will also end the simulation in that state. So a little more formally now, a state action pair is an action that can be taken from a specific state. So in our simple example here, our robot's going to have 4 actions that it can take from any particular state, up, down, left, right, or north, south, east, west, however you like to see it. And I've drawn some arrows now on the diagram here showing what the outcome of each one of those states is going to be if you take it from a particular state. Most of these outcomes are straightforward. The ones that we might expect, moving left moves us into the south to the left, and moving right moves us to the south to the right. I've also indicated that along the outside, around the barriers of this environment and also around that inner cell that does not have that is not a state that can be occupied, we kind of bounce off the wall. So if we keep moving as far as we can to the left here, and we move into this left wall, we'll just stay in that cell. We bounce off, and that's a typical thing that we might do in a reinforcement learning environment. We might even put a little bit of an ouch there, an ouch, you bump into the wall and you get a little bit of pain to tell you don't do that later, or learn, don't do those actions, mostly because they don't do anything. They're a waste of energy or a waste of time. As I mentioned, we're going to be focusing right now on a deterministic environment. That means that when we execute a state action pair in a particular state, there's going to be exactly one outcome as a result of that. So we're always just going to end up in one state. There's no probability involved, and there's sort of no non-determinism, meaning that there's not going to be the possibility for us to have more than one state as our outcome, and then there's also not going to be the possibility that we have 0 states as our outcome. Again, making this a little bit more formal, we can now take those state action pairs and we can define a transition function. We often use the lowercase Greek letter delta for this. And so we've got this function that's going to map from a state and an action, or a state action pair, and it's going to map it to the next state. What will the next state be as a result of that? In reinforcement learning context, we usually want the environment to be giving us this reinforcement, and we call it rewarding, or giving us a reward or a punishment when we enter a particular state. So usually in these types of models, we have the reward or punishment attached to the state. So by entering the state, you get a little reward or a punishment. This is the model that I'm going to use in our examples here. Getting the pot of gold is going to give us 100. Falling in the pit is going to give us minus 100. And then just entering any other state, we can usually set these to be 0 if we like, in which case we might say our environment is partially rewarding instead of fully rewarding. But in this case, I've added minus 5s. Now the reason I've put that there, a small little punishment for each state, is we might think this is, drain of energy to move into that state if that was something that our robot had. It's going to inspire our robot to try and take shorter pathways to the pot of gold, so it can kind of save that energy and maximize its output, or as we'll call it down the road, its utility. We can also formalize the reward function, and we can call it, in this case we'll call it R, and that's just going to be a one-dimensional function. It just takes the state and it tells us the reward. If we take the transition function and then we take the reward function and we put them together, we will often call this the model of the environment. If we understand the model of the environment, then there's a lot that we can do. And when I say we understand it, if we know the model of the environment, then that means we know all of these transitions and we know all of the rewards. We will say that our environments are knowable, fully knowable, or sometimes fully observable if the agent can learn the model by observing the world. And by observing the world, we usually mean trial and error, trying an action in a state and seeing what happens, see what state we arrive in. When we do know the whole environment, we're going to say that the environment is fully known. And we might distinguish between knowing this after we've done observation and also knowing this before we've done observation. If we know this before we do observation, then no observation is going to be necessary to learn the model. And in those cases, we can usually do offline processing. So if we have a fully known environment and we have the time to plan before we go into the environment, then this reduces to what we might call a state space search. And state space search is sort of a very traditional AI problem where we have a state space and we're just looking for the goal state and we're just trying to plan a path, sort of a path finding. That's why Dijkstra's algorithm is listed here. In this particular simple environment, if we knew that the reward for every state was -5 except the goal state, then a simple breadth first search would be enough to find the goal state here. There's also negative weights here, so we might want to run a different algorithm like the Bellman-Ford algorithm, or if we have a larger environment, we were interested in being a little bit more efficient, we might run the A star. There's lots of different options that we might have of algorithms that we could run to plan our motion or our path through the environment. If we already know the entire model, we know the whole environment. So part of what we're going to be focusing on is cases where we do not have the whole model known ahead of time, where we can learn them through a process of exploration and observation. And in my next video, I do want to look at that in a little bit more detail. But at the moment, I'll just say that it's a somewhat straightforward process where, as I've already hinted, you're in a state and you take an action and you observe the outcome. And if the outcome it brings you to a state, you record that. All it requires is one observation in a deterministic environment to make sure that you know what the outcome of a particular state action pair is. So if you can observe all of them, then you can learn the model. So this is just a simple example of that process. Maybe the robot will move to the left, observing both the transition function, where that arrow goes, and then also the reward for entering this state. And in both of these cases, we're assuming it's deterministic, so the reward is always fixed. It's always -5, it never changes. So after one observation, we know the reward for that state and that transition. We can now start talking about a sequence of states. I've hinted at the term utility, which is sort of the total reward, or the total amount of reward that the agent gets after performing some sequence of actions or states. At this point, I've said a sequence of states because every action is going to bring us to a new state, and we've attached rewards to states, not to actions, although in some models we can mix that up. But at the same point, saying a sequence of states then is going to be the same as saying a sequence of actions, as long as those are the states that correspond to a sequence of actions that are being carried out. So let's imagine we have a sequence of actions that our robot's going to carry out here: left, 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 up, up, right, right, right. And we're going to start off in this state, which originally we called this state 10. And we're just going to keep track of the rewards that we get as we go, and we're going to accumulate them in our utility. So we're going to start in this state. We're going to assume we actually get penalized for entering this state, which is the first state. So we'll assume that to start out that we had -5 as our utility and our reward for this state. So we can move to the next state, move to the left, following the sequence of actions that we have planned here. Moving to the next state, that state is state 9. Remember, all states have a -5 penalty, so -5 minus 5 is going to be -10. So continuing on, pretty straightforward, we move left again, we get another -5 accumulating to -15, and we continue. We move left, get another -5 to be -20. At this point, we're going to try and move left again, and maybe we bounce off that wall. We accumulate another -5 as a result of that, but maybe we'll assume that our robot doesn't want to do that again and maybe changes its mind and decides to move up. So it moves up now, and then we'll move up again. Maybe we can see the pot of gold. Of course, we assume our robot can actually see the pot of gold in that way, but maybe it's decided now, okay, I'm going to go to the right. At this point, we've accumulated a total penalty of -35 with 2 more steps right. Our total penalty is -45, but if we move 1 more step to the right, we will get our pot of gold. That's a terminating state or a final state, so that will end this sequence of actions. And after ending the sequence of actions, we can say the total utility or the total reward is 55 for this sequence of actions. Computing the utility that way is called the additive utility, and again, it's a very common way to do it, but it's also very common for us to try and add a discount to rewards that are going to be distant in the past or the future, depending on which direction you're measuring your utility. As I've got it set up right now, we're talking about the sequence of states that you might go through and then end up in a terminating state. So we're sort of looking back into the past. We want the most recent reward to be the one with the highest weight, and the one most distant in the past to accumulate the least or attribute the least to our utility. When we look into the future, so we're looking at rewards that we might get in the future, we want the rewards that we're going to get most immediately to be the ones that are discounted the least, and the ones that are the furthest in the future to be discounted the most. So to do this, we're in both cases calculating it is going to be the same. We're going to start at the rewards that are the most recent or the current ones, and we're going to move away from the present as we go, discounting as we go. So the previous sum that we had here was exactly the same. We were just going to sum up all the rewards, but in this particular case, we're now going to apply this discount factor gamma, and we're going to apply it to the power I. So the first one will be 1, so the most immediate reward, whichever reward we're getting right now, will get the no penalty at all. Otherwise, we're going to be applying a gamma that's in the range 0 to 1, which is going to diminish over time. Now, on the extremes are rare. We don't usually set them to the extremes because if it's 1, then we're just using pure additive utility with no discount at all. And if it's 0, then we're just saying that all that matters is the most recent reward. So utility completely discounts all other rewards. All that matters is the current cell or the current state. Again, both of those are really extreme, and it's unlikely that we might do that. So in our example, for instance, let's use a gamma of 0.9, which is kind of more common, which is sort of a discount factor that is less than 1, but maybe close to 1. So in this case, there's a lot of numbers that accumulate if we're calculating this out. So I just punched this into a spreadsheet, and I got the value 72.5. So what does that mean? Well, of course, utility has no units attached to it. We can think of it as goodness or units of value. But what matters to us here is more comparing it to the other additive utility that we just looked at. And the other one, we got 55. This one got 72, which is discounting the penalties we got more distantly in the past to get to this reward of 100. So you can see that the reward of 100, which is more recent, is being counted more greatly in this discounted utility than it was in the other. So we can now describe what we call a policy, which is a way to describe a plan or a strategy in a particular environment. That is, at each state that we might find ourselves in, we want to select an action that we think is the best action or the action that we're going to carry out if we're in that state. So a policy is a mapping of states to actions or state action pairs. And in this case, I've sort of given an example of one policy. In this case, this is the optimal policy. This policy tells us from each state which state we should move to if we want to get to the goal, which is usually what we want to do. Before looking at an optimal policy, even though this is an optimal policy, we can define the utility of a state with respect to any policy. So if we take a look here, what we've done is we've been using the reward function on the state. That was the example that we had before. Well, now what we're going to do is we're going to find the reward function, and we're going to apply it to the transition function. So all the transition function is going to tell us what state we're going to arrive at if we started in state Si and we apply our policy. Our policy tells us which state we should move to in state I, and then that transition function will tell us that next state, and that next state will calculate the reward. So this is an iterative process, so then we will do this again. We'll go to the next one. So starting at state 0, say that we start here where our robot is, we will move to the next state, following the policy, and then we will move to the next state following the policy, and we'll move to the next state following the policy, and so on until we get to a terminating state, and we would calculate that sum. It says go to infinity or until it ends. Follow that sequence by following the policy, and then we'll define that to be the utility of this state. So this state here, its utility will be dependent on following that policy in the states that we might end up in as a result. Because this utility ends us up in the pot of the gold, so the pot of gold will be in the future now, so it's a little bit distant. It's going to still contribute to the utility of this state, so this state should have a positive utility even though its reward is -5. And we'll take a look at that in a second. We're going to compute the utility of all of these states in a sec. So I mentioned this already. If a policy is going to then maximize the utility for every state, so in any state we're in, we have the policy that maximizes our utility for that state. We call that the optimal policy. We can compute the utility of the state relative to the optimal policy, because that's the policy we ultimately want to learn, using a value function or value function update. So here we just are going to be using the term value and utility somewhat interchangeably, even though there's going to be a subtle difference here. Utility is sort of the goal, the thing that we want to compute, whereas the value function is the tool that we're going to use to compute it. So let's take a look at this value function update here. This is going to be an important rule that we're going to modify a little bit down the road when we get to probabilistic worlds as well. So the value function is a function of a state. So each state is going to have a value function, and we're going to compute it by looking at the reward for that state. So we're going to take the reward for that state. Most states have reward -5, but the rest have, the goal states have specific rewards. Then we're going to apply a gamma, so that's our discount factor that we've been using in our calculation so far. We're not raising it to any power because we're only going to look one state away. What are we going to do? We're going to look at all the states around us, whichever state we're in, right? We're going to look at all the ones that we can reach. So that's what this first bit's saying. It's saying the maximum over all the A's, all the actions in this set of actions for this state. So we sometimes call this a set of, call the set of all the actions for a state a set, because each state might have a different set of actions. Now in my example, we all have north, south, east, west, or up, down, left, right for all of our states, and that's not necessarily true for all environments that you might have. Being in a specific state, you won't be able to shoot the gun if it's not loaded, for instance. Then that might be a state that you need to get into before you can carry out that action. So the actions that you might be able to carry out might be dependent on your state. In our example, no, but that's all this is saying here is take all the actions in the current set of actions that are available to you given your state and maximize over them. Pick the best one. What are we going to find? Well, we're going to first apply the transition function to that state, to the current state, with that action that we selected out of that set. And we're going to find out what new state we would be in, and then we're going to find out what the value of that state is. So this is a recursive kind of definition where we're going to define the value of this state with respect to all the value of the states all around us. So this transition function in our example is just going to find all the states we can move to, or the 4 directions that we can go, and then it's going to maximize over those values and apply our discount factor. So this value function update, this tells you how we can update the value function for a particular state. This is used in a couple different kinds of algorithms to try and compute the utilities or the value function for our problems, for our environments. So let's take a look at this example. We usually start with the goal states, and we apply in the goal state, since there are no states that they can go to after, we just apply their reward to be their value or their utility. Now there are 2 ways that we can maybe apply this. We can update the value function sort of over and over again and use that to hopefully over time it will stabilize all the states, and the states we'll know what our utility is. That's sort of a blinder way to do it. If you're a little bit more clever, you can compute back from goal states the utility, and that's what we're going to do here. That's sort of a dynamic programming algorithm. So after we know that this state has value 100, then the state moving back is now we can compute its value as well, or any state that is related, and next to this one we only have one, we can compute its value as well. This dynamic programming algorithm is very similar to Dijkstra's algorithm, so at this point this is going to be an estimate. We're going to just make sure. We might have to recompute it later if something's new information, but in our nice little simple grid environment that's not necessarily going to happen. So we're going to update that one and say, okay, this value is now correct, and like Dijkstra's algorithm, we're going to push back. We're going to see, okay, these two, again, all we're doing is applying this rule. We're going to see what's the maximum around us. Well, 85 is the maximum, and we're going to compute using our discount factor and making sure every time to apply the -5 penalty for that particular cell as well. And we'll just compute as we go back. Another 59, 48's in these cells, and a 39 in this cell here. And what we can see now that we're done is that the optimal policy, the policy that we have displayed there, is actually corresponding to moving into the cell with the highest value or utility, as computed by our utility function and our value function update. So this particular kind of update is very common in deterministic environments. Once we know the value of if we know the whole environment as we did here, then we can just compute this update to figure out what the optimal policy is. All right, so I've actually got a simple implementation of this. So even though we just carried this out by hand, we've got an example of our little world here. This is with our value functions all set out to be 0. And we can also, for instance, show the reward attached to each of our states. And then if I compute the value function, it will compute the value function for us. I've got a couple other setups here, so let's take a look at our maze setup here. So this will be a maze setup. Again, the top value here is going to be the reward for each of our cells. We've got a pot of gold down in the corner, and we can just calculate our value function here, and that's going to compute the values for each of our states. And if we want to show our solution as well, we can now see which direction should we move if we want to get to the pot of gold, and it will tell us which direction we should move from every particular cell in the maze. So again, all of this is computed offline. No observation of the world has had to be done because we're assuming the world is known ahead of time in this case. In my next video, we're going to take a look at that. We're going to take a look at how we might explore the environment if we do not know it already. So maybe we'll turn our fog of war on, we'll reset our values, and we'll set an agent out into the world that will explore the world. So next video, we'll take a look at how this agent might explore. So I want to thank you for watching this video, and we'll see you in that next video.